Okay, so now we're going to look at a situation, two situations where we work with samples for two populations, and we want to get some information about those two populations. And so we're going to do some samples of each population, two populations, two samples of each population. And then we'll make inferences about the population based upon the sample. And these two situations are going to be where the population standard deviation is unknown in each of those populations. And so again, we're going to do kind of what we just did before, an interval estimation and then a hypothesis test. And so we'll look at the interval estimation in this one. And we have some formulas to help us out here. So when the population standard deviations are unknown, we'll use the sample standard deviations as estimates of the population standard deviations, and we'll replace z with t. And so again, to do an interval estimation, you're going to have some point, and then that's going to have some margin of error. And the margin of error is like the plus or minus part, like, hey, with a certain margin of error, our data, the population data with a certain amount of confidence will be in this margin of error. And the margin of error is made up of some value and some quantity of that value. So some value, which is our standard error, and that's standard deviation, the standard deviation of a sampling distribution. And then, so we have some amount and then a quantity of that amount. And that quantity will be z if our population standard deviation is known, and it'll be t if our population standard deviation is unknown. And so some of the stuff we've already seen, but the main takeaway is like when your population standard deviation is unknown, you're going to work with t, and at least that's what we've seen so far in the course. And when your population standard deviation is known, you're going to work with z. And so there's a t distribution and a z distribution. We're going to look at that in a second and just kind of familiarize ourselves with the differences between that. And I have a resource to share with you. And so to work with the population standard deviation unknown and to work with t as opposed to z, we need to know the degrees of freedom. And so we'll use this formula down here for that. And so sample standard deviation is the s, the lowercase n is the sample size. And that's pretty much everything you need to know here to put all that stuff in and calculate it. And same thing up here. All right, so that's how we get our interval estimate. It's some point plus or minus some amount, and that's the margin of error. And this is the standard error, so this is the margin of error, some quantity, some amount, and then a quantity of that amount. And so this amount here is the standard error, standard deviation of the sampling distribution. And then this is the amount of that we need. And so here's our problem, Clearwater National Bank. And you could read through this, but we've got two bank branches, and we do a random sample of 28 checking accounts and 22 checking accounts. And we get a sample size, a sample mean, and a sample standard deviation. We should probably add deviation in there. And, it somehow ended up on that line. Well, let's take it out of that line. That's better. So those are the numbers right there. And so we want to develop a 95% confidence interval estimate of the difference between the population mean checking account balances at the two branch banks. So we're going to, 95% confidence interval. What's the difference between the population mean checking account balances at these two branches? And so then we have to do all of our math. We get our point estimate of the difference between the population means. And to do that, we take a difference between the sample means, and that gives us this value right here. And so it's 115, right? And then we calculate our degrees of freedom, so all of those numbers get plugged into this. And if we look at this side by side, I'm just going to open this up and then bring this over here and move it over to the right and bring this one over to the left. So if we look at our problem right here, and we look at this right here, we can see 28 and 22 are in. It's the lowercase n, the sample size. You can see where 28 and 22 have been plugged in there. And then we also have to plug in our sample standard deviation. And that is 150 and 125. So you can see the 150 and the 125 got plugged in. So you just get all those plugged in, and you get 47.8. And then that gets rounded down to 47. So that's how that got calculated. And So we have 47 degrees of freedom, and then with 47 degrees of freedom, we need to go to our t-table, right? 47 degrees of freedom, and then our alpha divided by 2 is going to be 0.025. And so our alpha is our level of significance, is our alpha. And so we have a 95% confidence level, which is a level of significance of 0.05. And so let me just bring this back down here. And so we're on the wrong one. This is the one we want to be on. And so that's going to be like, 95% confidence, 2 tails, and the alpha is in each tail. So 5% divided by 2. So you have 0.025 in each tail, or 2.5% in each tail. And now let's take a look at the difference between the z-table. So here's from the back of the textbook. This is the z-table. And here's the t-table, right? So t-distribution. And so in this one here, you can see that the z-value is on the left and the top. So it's the row header and the column header. And if we were to do 1.96, which would be like, it would be 95% confidence with 2.5% in each tail, which would mean that we'd have at that 1.96, from this point to 1.96 standard deviations away from there, we would have from this point over to the left 97.5% of our data. So that's the probability, right? So this gives us the probability, the area under this curve from this point, 1.96 standard deviations from that point right there. It gives us, 97.5% of our data from here over, and 2.5% would be in the tail. That's how you read the z distribution for, cumulative probabilities for the standard normal distribution. And if you read this here, entries in the table give the area under the curve to the left of the z value. For example, for z 1.25, 1.25 would be right here. The cumulative probability is 0.8944, so 89.44% of the data would be from here to the left if our z value was 1.25. And then over here we have the t-distribution. I really like this table a lot better than the one I was using online that I just found online, which is why I finally just took a picture of the book. And these tables are listed for you in Module 0, so you could download these tables and work with them from Module 0. And if you look at this one here, we have degrees of freedom in the left column, and then we have area in the upper tail. So these are the row headers. These are rows, and that's the row header. These are columns up and down, just like columns in front of a building, and these are the column headers. So here, the t-distribution is different than cumulative probabilities for standard normal distribution, which I think of as the z-table, and I think of this as the t-table. And so two different tables, and similar but different, right? And degrees of freedom are over on the left, and area in the upper tail is over on the right. So if I go over and I open the next t-table image, so if I go and open up T2, and I'm just going to open that up and then bring that over to the right, and we'll keep that one on the left so we can compare it to, that's not the one we want on the left, so I want that one on the left. There we go. So here's the z. You can see z right there, and here's t. And so for this problem here, we have 47 degrees of freedom, and we have an alpha of 0.025. Okay, so we have 47 degrees of freedom, 47 right there, and we have an alpha of 0.025, and so that's right there. And so we have 2.012 at 47 degrees of freedom, and area in the upper tail. And just notice here that with t-distribution, let me bring up the z. Well, there it is right there, right? That's the area in the upper tail, is that 0.025. And so entries in the table give t-values for an area of probability in the upper tail of the t-distribution. For example, 10 degrees of freedom and a 0.05 area in the upper tail, t is equal to 1.812. So just notice how this is different than the z-table. So we're just going to bring this back over and then grab the z-table, right? And they just work differently. So pause the video and try to wrap your head around that. And just spend a little time reading this and looking at how these work, and this, and looking at how these work. But in each of these, we're getting a z-value here, 1.96, and we're getting a t-value here. So on this one, I'm going to bring up the second image. So there is, that's not it, that's not it, that's not it. Let me see if I can go the other way. What happens? There we go. And I need 4.7. And so here we get a z-value, 1.96, and that's based upon some probability. Here we have the probability of some area. This is the upper tail. And we have degrees of freedom. And then we get a t-value. But whether you get a z-value, like going down here and you go 1.9, and then up here and 0.6, that's your z-value, 1.96. Or you get a t-value, you go here, 47 degrees of freedom, you go 0.025 in the upper tail, 2.012. That t-value and that z-value both operate in a similar way. And the way that they operate in a similar way is that when you're calculating your margin of error, it's some amount and then a quantity of that amount. So some amount is this stuff here, and then how much of that amount do I want? What quantity of that amount do I want? Do I want 1.96? Do I want 1.96 of that amount, the z-value, if I'm working with a population standard deviation known and I'm using z-values? Maybe that amount will be 1.96 here. I'll have the z. Or if I'm working with t and 47 degrees of freedom, and it has 0.025 in the upper right tail because I want the 95% confidence level, then maybe the value I'm going to use is 2.012 right here. Give me this amount of this. So this is some quantity, and this is the amount of that quantity that you want. This is the standard error, the standard deviation for the sampling distribution, and how much of it you want. 1.96, 2.012, right? So that's the difference between t and z. And t, what we've seen so far in the book is that you use t when the population standard deviation is unknown, and you use z when the population standard deviation is known. And so you get some amount of some quantity, and 2.012 is what they have. That's what we said. 2.012, 47 degrees of freedom, 0.025 in the upper tail, 2.012. So we get 2.012, and then we stick that in here, and we say, hey, here's my difference between the sample means. It's going to be that amount plus or minus this quantity of this. And so when you do this, you get 78. So it's 115 plus or minus 78, which means our range is our confidence interval, right? Our confidence interval, let's just look at the thing. Confidence interval or interval estimate is this amount here, right there. $37 to $193. So we're 95% confident that the difference between the mean accounting checking balances maintained by customers at this branch and that branch is $37 to $193. So that's working with making inferences about the difference between two population means when the population standard deviations for each of those populations is unknown. All right, so again, what we're learning here is we're learning tools, and they're tools for different situations. If you got to pound a nail, you got a tool for that. It's a hammer. If you got to drill a screw, you got a tool for that. It's a drill. So you get the different tools for the different situations. And now if you need to make inferences about the differences between two population means and the population standard deviations are unknown, I just read through that really quickly, you got a tool for that. And you could say, well, with 95% confidence, the difference between the mean account checking balances at the two branches is between these two. So that's what statistics is. You're learning these different tools for different situations. So here's the tool, and here are the formulas for dealing with this situation. See you in the next video.